Okay, this is the last video about discrete probability distributions. We will go over the last three probability distributions, the geometric, negative binomial, and Poisson. In the geometric case, it is way different than the binomial and the hypergeometric probability distributions, because in those two previous probability distributions, the random variable was the number of successes in a number of trials or in a sample size. Now, in the geometric case, the random variable refers to the number of the trial on which the first success occurs. So here, the random variable is not counting number of successes. It is the number of the trial on which the first one occurs. That's why the equation here is P, which is probability of success, times Q to the power of x minus 1. Now, what is the meaning of that? Since there is only one success, then that's why P is to the power of 1, and x minus 1 refers to the number of fails. There is no need to add combinations in this equation because the success is always at the end. It occurs always at the end or in the last trial. So we have equations for the expected value and the variance. Let's check this example. For a certain manufacturing process, it is known that on the average 1 in every 100 items is defective. So what's the probability that the fifth item inspected is the first defective item? So first thing, let's define the random variable. So it's number of inspected items. So again, it's not number of successes, number of inspected items, number of trials. Number of inspected items until the first success or until the first one defective is found. Alright, so here we want to find the probability that x is equal to 5, right? That the first defective is found at the fifth inspected item, right? So that's x equal to 5. So the probability of success or the probability of finding a defect is 1 over 100. Therefore, the probability of a fail, it's the complement, right? 1 minus 1 over 100. Now, since the defective one is found in the last in the last item inspected, then there are 4 units that are good, right? So this is the probability that is not defective, and the last one is the defective one, right? So times 1 over 100, right? So that's going to give us the probability that the first success or the first defective will occur in the fifth inspected unit. So that's the geometric probability distribution. Now, the next probability distribution can be considered as a generalization of the geometric one. So in the negative binomial, again, the random variable is not the number of successes. It is the number of the trial, but now on which the kth success occurs. So when k is equal to 1, so it's number of trials or number of trials until the first success occurs if k is equal to 1. So that's the same as the geometric probability distribution. But if k is equal to 2 or more, then of course this is negative binomial. So the whole idea here is like, okay, your random variable will capture how many trials will occur until you get the kth success. So here we need combination, because the k success they can be obtained in different positions, but the last one it's always a success. That's why we have the minus 1 here, because the last in the last trial we will get the kth success. And of course p to the power of k, that's the number of successes, right? And x minus k refers to the fails. So the expected value is k over p, and the variance, we are given an equation in terms of k and p. Remember, k, number of successes, p, the probability of success. Alright, let's check this example. In an NBA championship series, the team that wins 4 games out of 7 is the winner. That's like the normal way in which most of American sports are. Even baseball works in a similar way in the playoffs. Okay, so suppose that teams A and B face each other in the championship games, and that team A has a probability of 0.55 of winning a game over team B. So we will assume that this probability will remain the same regardless of the game that they are playing. The first question is A. What's the probability that team A will win the series in 6 games? That means to find the probability that team A will win the 4th game or will win 4 games in 6 games, right? So X, random variable, you always have to define the random variable before you proceed. Will be, in this case, number of games until 4 wins, right? So in how many games you get the 4 wins? So this X, the minimum possible value is 4. It's not possible to win the series in only 3 games because remember, one team needs to get at least 4 games, right? So the minimum value is 4 and the maximum value is 7, right? It's the best out of 7 games. Then in part A, we're being asked about what's the probability that the random variable for X is going to be equal to 6. That means getting 4 successes in 6 trials or in 6 games, right? So let's use the equation. So this is equal, this is x minus 1. From that we take k minus 1. For x minus 1 that will be 5, k minus 1 that will be 3. So from 5 we take 3. Then the probability of success, 0.55. Number of successes, 4, right? And the number of fails will be x minus k. So that will be this is the complement to the power of 2, right? So you will get that the probability here of team A will win the series in 6 games, in exactly 6 games, is 0.185. And now the next question is what's the probability that team A will win the series? That means that team A may win the series in 4, 5, 6, or even 7 games. So we're being asked here to get the probability that x is greater than or equal 4. So as I said, this is probability of x equal to 4 plus probability of x equal to 5, 6, up to x equal to 7. So if you get individual values using the same equation, you can use even the cumulative, the CDF. This is equivalent to F7 minus F3. It's the same thing, right? Or you can just get the individual values. And at the end, you will find that the probability is 0.608. That's the probability that team A will win the series, which is greater than 0.5 because in every individual game, A has like a small h, right? It's 0.55. So it has a greater chance of winning a game and of course of winning the series compared to team B. Okay, now let's check the last probability distribution. Is the Poisson probability distribution. So in this one, the random variable is defined as the number of occurrences per unit of time or per unit of a specified region, such as meters or kilometers or volume or any other unit. So a typical example of the Poisson experiment is if we analyze a call center. So the number of calls that they get per hour, that's an example of a Poisson distribution, a Poisson variable, because we're counting number of occurrences per unit of time. It's like a rate. It's like a rate. Same idea if you analyze a bank or a supermarket or the library. We may count the number of students or customers that are arriving to the building per unit of time, per minute, per hour, per day. So every time we count something per unit of time or length or any other region, then that's an example of the Poisson distribution. It has some properties, so one of the properties is the memoryless property that mentions that whatever occurs in one interval won't affect another interval. Alright, so random variable, as we just said, is number of occurrences per unit of time interval or specified region. The main parameter that we use in the Poisson distribution is lambda. It's the average rate of occurrences, right? So lambda, in general, it's a rate, number of occurrences per unit of time or length, or any other possible interval. This is like it's a rate, it's an average value. Okay, so the equation for lambda, for the Poisson distribution, if we want to get an exact probability, it's E, this is Euler, to the power of minus lambda t. T is the length of the interval. If it's 1, then t is equal to 1. If not, you will need to modify. Then times lambda t to the power of x divided by the x factorial. One of the nice things of the Poisson distribution is that the expected value is lambda t and the variance is the same, so it's easy to remember. The shape, it's positively skewed. Let's check a couple of examples. So in the first one, during a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. So what we're getting right there is the lambda, it's the rate, the average rate. 4 particles per unit of time. 4 particles per millisecond. Then the question is, what's the probability that 6 particles enter the counter in a given millisecond? So x, random variable, it's number of particles, it's a discrete variable. In this case, in 1 millisecond, so per millisecond. Okay, since the question is being asked 6 particles in 1 millisecond, in a given millisecond, then the interval of the analysis is t equal to 1. So having said that, then we want to find what's the probability of getting exactly 6 particles in 1 millisecond. Then we just plug in the values, lambda, and the x value, right? T is equal to 1. Therefore, the probability of getting exactly 6 particles through the counter in 1 millisecond, it's 0.1042. So if for any reason, in a different example, we're asked to find the probability for the same number of particles, but in 2 milliseconds, then in that case what we're changing is the interval, t. In some books, even they don't use t, they use, in the equation you will see only lambda, and that's it, t is not included. So if that occurs, if you see something like that, it's not a big issue. You just have to adjust lambda in case the interval changes. So you just multiply by t, and that's it. Alright, let's explore a second example. It says 10 is the average number of oil tankers arriving each day at a certain port. The facilities at the port can handle at most 15 tankers per day. What's the probability that on a given day, tankers have to be turned away? So first thing that you need to define is what is the random variable here. The random variable is number of tankers per day arriving at the port. So it has it's per unit of time. Number of occurrences per unit of time. We know lambda, the rate, is 10, right? 10 tankers per day. And the question here is that what's the probability that the capacity is going to be exceeded, right? Because they can handle at most 15 tankers. So what's the probability that they have to turn away tankers? So what we are being asked here is what the probability of x is greater than 15. That's the probability that the capacity is going to be exceeded, right? Then the problem here is that we don't know what is the maximum value. So if you try to find the probability with the equation, that will be probability of x equal to 16, 17, 18, and you have to keep going until you start getting some small numbers, like almost close to 0. Or it is easier to just use the complement idea. So what is the complement? This is equivalent to 1 minus the probability of x less equal than 15. And this is what we call the CDF, right? The cumulative distribution function. That's why the CDF is important, because you will find, for these probability distributions, you will find tables that will help you to compute that CDF, or even in Excel, we can find it easily. So this is just the sum of the probability when x is equal to 0, 1, 2, 3, up to 15, right? So 1 minus that will give the probability that x is greater than 15. So from 16 and greater. Then if we find the values, this is 1 minus 0.8516, which is equivalent to 0.0487. Okay guys, this is everything in this video. During the session we will practice how to use the tables, how to use Excel and R to compute these probabilities. I'll see you in the next video.